Greetings once again, AP Calculus students. Mr. Record here from Avon High School. Continuing to look at our Continental Mathematics League problems from Meet 2. We're in the 2020-2021 season. We're going to look at problem number 8. Remember, problems 7 and 8, always a little bit more challenging as they're both worth 2 points apiece. And so I'm going to slide my camera over here and then we're going to read the question here together. It says, sand is draining from the top half of a conical hourglass 6 inches high and 4 inches in diameter into a cylindrical can with a radius of 4 inches. The depth h of the sand in the hourglass is changing at a rate of h minus 6 inches per minute. Y is going to be the depth of the sand in the cylindrical can. At what rate is y changing in inches per minute when h is 3? And fortunately, we are given the equations for both the volume of the cone and of the cylinder. Now, I think there are 2 different related rate questions that are in this series of videos that maybe you have checked out my previous one on I think it was on the 2022-23 exam. One of the 2 problems that I have in the, one of the videos I made was for a rate in and rate out, had to do with, I think, a cube expanding. Well, I'm going to treat or attack these problems in a very similar fashion. I always like to draw a picture because, hey, a picture is worth 1,000 words, right? And then we're going to have our typical given information, our find information, and then I guess as far as the equations are concerned, I don't know if I really need much by way of those. I'll go ahead and write it because the equations are given to us there in the stem of the problem. And so let's see if we can get a handle on what's going on in this picture. A conical hourglass. That's kind of funny, isn't it? A conical hourglass. Well, I think what's going on is that we have a cone shape. It's not much of an hourglass, but it's kind of like the top half of the hourglass, I suppose. That would look like this. And then sand is able to fall out of a small opening there in the bottom. And then it's going to end up basically pouring itself into a cylindrical vessel. So it's not your typical type of hourglass or any one that I have known of, but that's what's happening from a picture standpoint. We know that this cone, it says, is 6 inches high, so I'm going to label that with 6. 4 inches diameter. You got to be really careful with that. 4 inches in a diameter is going to translate to 2 inches as a radius. And to be honest, you are much more interested in radius values than you ever are in diameter values because of the 2 equations both have r's in them. What else do we know? The cylindrical can has a radius of 4, so this is actually a radius, so I'm going to label it as such. And it says the depth h of the sand in the hourglass is changing at a rate of h minus 6. So I'm going to go ahead and call a little bit of sand. Let's put some sand in this hourglass. How about that? That's some sand. That'll work, won't it? Brown sand in that hourglass. And it says that that's going to have a height of h. Now, when you look at the information here that's given, okay, sand's falling out into this cylinder. It says that the depth h in the hourglass is changing at a rate of h minus 6. Well, I think that that is your given. The fact that the rate of change of the height of the sand h is changing at a rate of h minus 6. Now, I know that that is not the normal rate of change that we would like to see in our given equation. I think we would want that to be a number, but it's something that we really don't have much choice with. We're going to have to use it. And it asks us to find out at what rate is y changing. Now, I did not label y over in my picture, but there's still time to do so. And it says that y is the depth of the sand in the cylinder. So I'm going to call, let's do a better job of this. Let's say that, oh, eventually there's going to be sand down here, and it's going to be the same color, of course. So let's give me just that much sand. And so that part there, as it increases, is going to be my y. H is going to get smaller and smaller, right? Y is going to get bigger and bigger. And Kind of makes me think a little bit about, this this notion in this problem of me using h minus 6 uh, for the rate of change of the height of the sand. Um, should it be the opposite? Should it be negative h minus 6? That's a really good thing to ponder. And it turns out that we're going to be able to work this out when the time comes. When we look at the final answer, there's a certain value that we want the y to be in terms of, is it positive, is it negative? And we'll kind of revisit that here in just a moment. What are we trying to find? Of course, at what rate is y changing? And so that's certainly going to be dy dt. And yes, your equations are already up there, of course. And I want to start with this idea of the cone, volume equal 1/3 pi r squared h. And the problem kind of gives us a hint here. It says, first find the derivative of the volume of the cone. Well, okay, I suppose we could do that, but we have a bit of an issue. And that issue is the fact that we have both an r and an h in this formula, and we've never ever liked to have more than one variable in our related rate question, because we want to take the derivative with respect to our t, of course, and having to deal with a dr dt and a dh dt is just too much. We would like to see if we could get one variable in terms of the other. And we are going to be able to do that if we're very careful. And that is by using a relationship that equates the r and the h. And you've seen this many times in other problems that we've solved. So I'm going to kind of lay the groundwork here for this. I'm going to look back at my picture, and I'm going to take a cross section of this cone, of this hourglass, and I'm going to move it out from the picture here, right? Just there it is, right below me. How you doing there? And I'm going to notice that the top is still going to have a distance of 2, and the vertical portion of it is going to have a distance of 6. Now, if we do something quite similar, but to our sand portion, like that, we can extract him from the picture. We notice that that's going to fit so snugly right there that we have what kind of triangles here? You guessed it. I heard you. Yeah, similar triangles, right? We have angle-angle similarity. They both share a right angle, and they both, by the reflexive property, share the angle that's in the bottom. And so that means you can set up all sorts of proportions. Now you have to get the dimensions of this circle set, and we've already stated that the height is just unknown as h, and this r value, radius, is going to be an r, because notice, guys, this changes, right? As the level of the sand gets shorter and shorter, the h becomes smaller and the r becomes smaller as well, and they do so in a very similar proportion. And so from this point here, you can set up a variety of proportions. I'm going to start with 2/6. Now you're locked in. That would be equivalent to r/h. And now we want to cross multiply. And as we're doing that, we want to start to think about, what would be the best variable to solve for? And the answer is going to be the variable that you don't see very often in your given and in your find and in your equation. And just to add a little bit more to this find, remember it says at what rate is y changing when h is 3. Maybe that's going to be enough to kind of hammer this point home. But it looks like we see 2 instances of h. We see one here and we see one there involved in the given. So h looks like it's good, r looks like it's not so good. And so let's go back to this equation and we're going to solve it for r, which I believe is going to give us h divided by 3 after we reduce. And so now our volume formula for our cone, probably ought to put cone here because there's 2 volume formulas, is 1/3 pi. Radius becomes h/3 squared times our h. Now, we're not quite out of the woods yet because we're still going to have to take the derivative of the cone and somehow move ourselves into the cylinder world. And in order to take the derivative of this cone, we want to do it as easily as possible. So by all means, you guys, spend a moment, do some algebra here, right? We're going to go ahead and square out this h over 3 to get h squared over 9. And then if we work on this just even a little bit more, we're going to come up with what? Pi over 27 times h raised to the third power. And oh my gosh, what an easy thing to take the derivative of. In fact, I'm going to go ahead and do that right now. Derivative of the cone with respect to t, as we're trying to find up here, is pi times 3 over 27, or pi over 9, h squared, tack on the dh dt. Okay. Now, what does this have to do with the y? Because the cylinder, and I'm going to write this over here, the cylinder has its own volume formula, pi r squared y, right? And again, if that r is bothersome to you, we're going to have to rename it something. But here's where you've got to be careful. You don't want to call this h over 3. That's so important. Think about it, guys. You're in the cylinder now. What is the radius of the cylinder? It's the constant 4, right? Make things super easy on us there, right? So the volume of the cylinder is just 16 pi y, right? 16 pi times y. Well, if we take the derivative of this, thinking, well, we're going to probably have to do it eventually, it's a pretty easy derivative, right? 16 pi, and then the y there is going to require a dy over dt, which, alas, is what we're trying to find, right? But notice, we cannot find that dy dt unless we know the rate of change of the volume of the cylinder. Well, the sand that's coming into the cylinder has to come from somewhere, and it's coming from the cone. So whatever you get here is going to play a very prominent role over here. How do we find this volume of the cone? Well, I think at this point you've got enough information. You've got an h, you've got a dh dt. The only other thing I want to warn you about is if sand is falling out of the cone, that means the derivative rate is likely going to be a negative number. Sand would be coming into the cylinder then at the positive of that same number. In other words, sand's not splattering out on the ground, right? It's all going into the cone. So if you have to think about that or rewind the video and kind of listen to that statement again, feel free to do so. But you've got enough information to get going with the problem. I know the answer is going to be some fraction value between 0 and 1. It's a little bit closer to 0, but that should give you enough information. Anyway, I hope this helps. We'll see you in the next video.